and I am here.
Okay.
And so, should we have a 30-minute session today? I checked it over with my mom.
Yeah, if that's all you feel like you need, let's just do 30 minutes.
Yep.
Okay.
Yeah.
Is that going to be standard on Wednesdays, or are we going to play it by ear?
What was that?
Is that going to be standard on Wednesdays, or sometimes we're going to do an hour, sometimes half an hour?
If I find something that I'm learning hard,
okay,
maybe we could do 30 minutes of going over what I'm finding hard, and then, or if what you're teaching me is really hard.
Okay, cool.
Like
I love this. This just occurred to me. This is a unique experience for me, where I get to take somebody and teach them algebra from scratch. Although a lot of this stuff you know already, it's not brand new to you. But this is
not a ton of it.
This is the next spot, the next subchapter in chapter 5. Let's talk about matching functions with their graphs. Which chart here is function A?
I'm not sure.
Okay, function A is y equals mx plus b.
Oh, okay, so, B.
Okay, good. When they use terminology like f of x instead of y, there's a good reason for that. And
no, actually it would be C because it's a downward slope.
No? You got it right. It would be, well, the first thing you look for is the y-intercept, which is first of all, it's linear, so it's a straight line. So it's either B or D. And which one has the y-intercept at -3? B. So that settles it immediately.
Oh, okay.
Okay? But it is worth noting that this is linear, this is linear, this is quadratic, and this is quadratic. Okay? But just let's talk for a moment about function notation. Because what you're used to seeing up until now is y equals 2x minus 3.
Yeah.
So why do we change y to f of x? Well, f of x merely means that we have a function of x. In other words, the function that's being defined is not a function of z or q or r, but x. Okay? And the reason that's better is to define it like that is that now I can ask questions like, well, what is this function when x is equal to 4? And I can say f of 4. That means 2 times 4 minus 3. So that would be 5. Whereas if I'm using y notation, I can't do that. In other words, I can't say y of 4. The only thing I can say is, what is y equal to when x is equal to 4, separately like that. But when you get into higher mathematics, this kind of notation becomes pretty important to be able to use. So that's the whole thing about f of x. Doesn't matter if it's a different letter. G of x just means a function of x.
So just something of x.
Well, let's say that I would, if I really want to get complicated, that means I have a function of x and y. So I might have that. See the difference? If everything on the right side contains one variable only, then it's a function of that variable. If everything on the right side contains more than one variable, it's a function of two variables. Two variables, you're a long ways away from that. I mean, we're not going to get to two variables until you're a college student, probably. But if I said I have a function of z, then everything better be z over here. In other words, that would not make sense. To say I have a function of z that's equal to 2x. It's got to be equal to some kind of z.
Yeah.
Okay? So that's notation. And it doesn't matter whether it's f, g, h. It all means the same thing. J, it just means you can always say that, you can always pronounce that a function of x. Okay? So this one's linear. We figured out that it was b. Is this linear or quadratic?
That's pretty much mx plus b format.
That's linear. That's linear, meaning it's a straight line. These are straight lines. These two over here are curved lines. So if it's not linear, it's going to be curved. The only thing that is a straight line is linear functions. So if I look at C, it's called a quadratic because it's an x squared minus 1. Which one is C? Which picture?
I'm pretty sure C is C because if you take x squared, it's not going to be as wide.
Okay. It's not bad logic, but let's talk about logic of graphs for a moment. How do I know what the y-intercept is when I have a quadratic? What is x when you're on the y-intercept?
When you're on the y-intercept, x is 0.
Yes. No, that's exactly right, and that's what you want to memorize. When you're on the y-intercept, x is 0. When you're on the x-intercept, y is 0. So in this case, if we want the y-intercept to distinguish between these two curves, set x equal to 0, and what's the function equal to?
It equals -1.
And that's this one right here.
Oh. Okay.
What is the y-intercept of D?
It would be, it is 2.
No, plug 0 in for x.
Oh, of D. I thought you meant D, the graph.
Oh, right.
Okay. So, it is -3.
Notice that it's at -3. Now, you did mention an interesting property about parabolas. This is a parabola, incidentally, as opposed to a straight line. And the fact that this is fatter than this one. This one has a 2 in front of the x squared. And that's why this one is skinnier. When you put a number greater than 1 in front of the x squared term, you make the parabola skinnier. If you put a number, in other words, if I have, this is my normal parabola, which is y equal x squared. Well, if I want to know what y equal to x squared is, one way to think about it is, well, if I had a point right there on the parabola of my y equal x squared, well, where's that point going to fall on y equal to x squared? Twice as high, right?
Yeah.
So I could go along here. Every point I find on my original parabola has to be twice as far away from the x-axis. What results from that is a skinnier parabola. And a fatter parabola, if I made this 1/2, in other words, if I use numbers between 0 and 1, gives me a fatter parabola rather than a skinny parabola. If I stick a negative sign in front of that, what happens? What are the consequences of that?
Wouldn't it, instead of going down then up, yeah, it would go up and down.
Exactly. What that actually is a reflection about the x-axis. A mirror reflection.
Yeah.
Okay.
Pretty much, I always get this screwed up, but it would be a horizontal, right? Horizontal?
What would be?
Horizontal image?
You're talking about what function would create that?
No, so it'd be a vertical reflection.
Well, it's not really called a vertical reflection, although that would be the word you'd put on it if you wanted to put a word on it. It's called a reflection about the x-axis. Okay? In other words, that would be a reflection about the x-axis. I can also have reflections about the y-axis. You won't see it with a quadratic, but if I reflected that straight line about the y-axis, it would become that. And you get reflections about the y-axis when you have the negative sign inside the function rather than in front of the function. Gosh, you haven't had enough functions yet that I can think of a function that you would know that we could see. Are you familiar with this function, y equal e to the x? You ever heard of it? Looks like that.
I can't say I have.
E is just a number. Let's use a number 2. Y equals 2 raised to the x power. This is called an exponential expression. It's not really an algebraic expression. But if I wanted to know what y equals negative 2 to the x would be, well, I would reflect that about the x-axis. It would look like that, right?
Yeah.
Okay. But if I put my negative sign in front of the x up here, it doesn't reflect about the x-axis, it reflects about the y-axis. So this curve would then look like this. So depending, when you put a negative sign in front of an elementary function, you get either a reflection about the x-axis, what you would call a vertical reflection, or you get a reflection about the y-axis, which is a horizontal reflection.
Is there such thing as a intermediate?
Well, there's a reflection about the origin. In other words, that's called an odd function, which is symmetrical about the origin. And let me show you one of those. If I take this function right here, which is y equal x cubed, that is said to be symmetrical about the origin, which means that if I reflected it about the y-axis and then again about the x-axis, this is what I would get down here. In other words, if I took this part right there, reflected it about the y, and then reflected it about the x, I would end up with the lower half of it. That is said to have symmetry about the origin. And they even name that. Those are called odd functions. Even functions have symmetry about the y-axis. If I plot y equal x squared, I get not that, but I get something that looks the same to the left of the y-axis and to the right of the y-axis. This has perfect symmetry about the y-axis. So if I were to stick a negative sign in front of this, inside the parentheses, doesn't change. In other words, if I reflect this function about the y-axis, it looks exactly the same, and in fact, it is exactly the same.
Okay.
Just some good stuff to know. Let's see, what else? They didn't have a lot in this part of the, this is it for this sub-chapter. So let's go. Let's see, that was function notation. Let's look at special functions. Have you ever heard of a piecewise function?
Of what function?
It's called a piecewise function.
No, I have not.
Okay. Well, here's a good example of one. Notice that it is two functions in one, kind of. Whenever x is less than or equal to 0, our function is x minus 2. This blue line right here. Whenever x is greater, excuse me, I said that incorrect. Hold on one moment. One second, David. Hello? Yes, it is. I'm in the middle of a tutoring session. Can I perhaps call you right back in 20 minutes? What's your name? Grace. What's your phone number first? Uh-huh. I'll be back very shortly. Thanks. Bye-bye. Wow. The phone is screwed up. Okay. Still there? Sorry. I said that wrong. It's equal to x minus 2 when x is less than or equal to 0, which is this lower blue line. And it's equal to a different function when x is greater than 0. It's equal to 2x plus 1. This line up here. Notice they have different slopes. This has a slope of plus 1. This has a slope of plus 2. They also have different y-intercepts. Also notice that this function has an open dot right there because it's x greater than 0. Has a closed dot right there because it's x less than or equal to 0. You with me?
Yeah.
What is the domain of this function?
The domain is...
And figure it out by looking at the function. Look at the function. I'm sorry, what?
Negative 3 to 2?
I can see why you said that. That's a good answer, except see these arrows? What that arrow means is that it goes on to infinity.
Oh, so
In both directions. Exactly, all reals. In other words, there is not a single value of x that you cannot plug in here. And you can see that by looking at it. How about the range? It's a little harder.
Wouldn't that be... That'd be all reals too, because...
How about this area right here? That's an area that y never achieves. It's never between minus 2 and 1. Yeah. Okay, so let me teach you interval notation for domain and range. Domain. Interval notation is like this. It goes from negative infinity to positive infinity. That's the domain. The range goes from negative infinity to what?
To negative 2.
With a bracket, because it can be negative 2. And then we're going to combine that, which is what that symbol means, with parentheses on this side. And what's this part going to say?
If there's parentheses on that side, that'd be 1 to infinity, right?
Yeah, exactly. Now, we always use parentheses next to the infinity sign, no matter what. And we use either parentheses or a bracket depending on whether it can be equal to that number or not. Since the range can achieve a value of minus 2, We have a bracket next to it because of that closed dot. Since this part of the range can never be 1. It can be greater than 1, but it can never be 1 exactly, just because that's an open dot there. In other words, when x is 0, this is what y is equal to, not up here. And so that range goes from 1 to infinity.
Yeah.
Okay, here we have a similar problem. Notice that it's a piecewise function. Y equals minus x minus 4. That's just a straight line. That's mx plus b format. It's this line right here. It's got negative slope, negative 1. Y-intercept of minus 4. And whenever x is greater than 0, y is equal to x, which is this line right here. Tell me the domain and range.
Domain and range of that. So the domain is anything because it's infinity on x, and then the range is negative infinity to 4.
Okay, look at the graph. To figure out your range, here's what I want you to do. I want you to put your eyes on the blue function line, start at the very bottom, and work your way up. In other words, like this. Put your eyes there, and when I say work my way up, I want to know what the y coordinate is as I go upwards.
Oh, I did not see that. Okay.
And here's the rest of the function. I'm going to put my cursor there. What's the y coordinate as I go along the function line?
All reals.
Is it, well, can we get below negative 4? Remember, there's not an arrow going in this direction. There's an open circle. That means it ends right there, or begins, however you want to look at it. In this case, I guess you would say it begins there.
Okay. So it'd be negative 4 to infinity.
Correct. Negative 4 with parentheses, or in other words, is it negative 4 to infinity like that, or is it negative 4 to infinity like that?
Would it be negative 4 to infinity like the first one?
The parentheses.
Yeah.
Because the open dot. And notice we don't really care if that's a closed dot anymore. Even if that was an open dot, it wouldn't affect our range at all.
Yeah.
We're still, well, exactly, right. Well, as long as this one was closed, it wouldn't affect the domain. If they're both open, if that's open and that's open, then x can't be equal to 0.
Yeah.
In other words, the domain would omit 0. It would actually look like this. The domain would look, as odd as this is going to sound, it would go, and you hardly ever see functions like this. In other words, that's the same as all reals except 0.
Oh, okay.
I had this function here. That's what the domain would look like in interval notation.
Oh. Okay, why don't we put the 2 there?
Because there's actually 2 ranges. In other words, in interval notation, if I graph that, this is what it graphs like. Well, there's this interval, and you don't cross over the 0, and then there's this interval here. So you have to combine them. Sometimes your domain or range will have 3 or 4 different intervals that are not continuous. So this merely means combined. We can go from negative infinity to 0, but we can't be 0 And then we're going to combine that with the separate interval from 0 to positive infinity. Okay. And you'll notice that they give the range. They're not using interval notation yet. This is a perfectly legitimate way to express range and domain. I have no problem with that. I just thought I'd introduce you to interval notation now.
Okay.
Okay, let's see. Only have 4 minutes. Sometimes you have a piecewise function. Notice that all of the piecewise functions here, the domain appears to be all reals. In other words, part of the thing is x greater than 0, the other part is x less than or equal to 0. So they're covering the whole domain, all reals with that. Same with that, same with that, same with this. Even this one here has 3 pieces to it. Let's graph number 5 real quick, just before we quit here, because we haven't dealt with 3-piece functions yet. So let me graph this one for you real quick. Okay, starting from the left, when x is less than minus 3, y is 1. You with me?
Yeah.
When x is greater than or equal to minus 3 or less than or equal to positive 3, it's x minus 1. Well, that's the line that has a intercept at 1. It has a slope of 1. So that is going to go from there to there. Straight line, closed circle, both ends, because it's less than, greater than or equal, less than or equal.
Okay.
And the third part is whenever x is greater than 3, to the right, y is minus 2. Well, minus 2 is there. Open circle, like that. So that's how we would graph that 3-piecewise function. Well, you don't really call it that. It's just a piecewise function. But notice, what's the domain of that?
Anything.
All reals. What's the range?
-2
Okay.
to, that looks like 4?
Well, let's analyze what it is. When x is 3, what is y? Plug in x equals 3 to figure out what y is.
Okay.
So that's 2.
Yeah.
And this point right here, which I didn't draw accurately enough, but that's also minus 2. So,
-2 to 2.
okay, minus 2 to 2, brackets or parentheses?
In
Brackets. Because of the closed dot.
oh, so if there's an open dot, it would be parentheses?
Yes, that's the difference. And it's parentheses whenever you have an equal sign with the inequality. It's a bracket, it's a bracket whenever you have the equal sign. It's a parentheses only if it's just a greater than or less than sign. Okay? One last thing before we leave. This function, do you know what continuous or not means? A continuous function is one that you can draw without picking up your pencil. Can I draw this? Right. I could not draw this without picking up my pencil. Therefore, it is not continuous. And that's all you need to know for now, the definition of continuity. Again, a higher math skill that you won't need for a while, but worth knowing. And we might as well talk about it when we're talking about piecewise functions, because those are the most common functions that are not continuous, or piecewise functions.
Yeah.
All right. Let's end it there, and we'll go on to the next subchapter next time.
Yeah.
Okay?
Okay, great.
Okay. So we're going to do, our standard is going to be Wednesdays for half an hour at 4, right?
Yeah.
Would it, I'm sorry, at 4:30. Would it bother you to do it at 4? Would it matter?
No.
Do you mind if we move it to 4?
Sure.
That way I can make it continuous between you and your sister, and I don't have a half-hour gap in there.
Yeah.
It'll help with my scheduling a little bit. So I will talk to you next Wednesday at 4, and I'll remind Sarah if you forget. When I see Sarah next week, I'll tell her to go remind you that it's at 4, not 4:30.
Yeah.
Okay? All right, David. Talk to you next time.
Yeah.
Bye-bye.
Bye.